Here's the companion for chapter 33. Shouldn't be a long one. Mostly I just want you to be exposed to this. This isn't an astronomy class, unfortunately, but it is a lot of fun to talk about this stuff. So, one thing that Edwin Hubble saw when he started measuring the distance to other galaxies and then their speeds is that, well, okay, first of all, he inferred their speeds based on the redshift of hydrogen lines. So back to quantum mechanics, hydrogen always gives off this very particular spectrum. There's a red line, there's kind of this greenish-blue line, and then there's some ultraviolet lines. Okay, so if you look at hydrogen in other galaxies, it surprisingly doesn't line up with the hydrogen lines from our galaxy, from a lab, basically. It is shifted, and there's only a couple of galaxies, both very nearby, that have, let's say, redshift. They have negative redshift. So this is their distance. The distance away from our galaxy and their redshift, usually given z. I know we've used that for so many different things, so we'll just call it redshift. So there are a couple of close galaxies, the Andromeda is one, that are actually blue shifted. That means that all of these colors are Doppler shifted toward the blue. That means that the Andromeda galaxy is coming toward us, and we are headed for a collision, it looks like. It looks like it's not moving side to side very much. But, you know, it's a long time away, something like 3 billion years or something. It's on the scale of billions of years, so it won't matter to us. But if you plot for other galaxies, the redshift versus the distance, you get this interesting curve that shows that the further you get away from us, the faster matter appears to be moving away from us. So, you know, Copernicus had this revolution where Earth is not the center of the universe. And then we found out that the sun is not even the center of the universe. The sun's just somewhere on the Milky Way's spiral arms. So here's the sun. Well, this appears to contradict this because looking at this graph, every direction we look, everything is moving away from us, and the further you get away from us, the faster things are moving. Okay, I messed up on that arrow. So it appears that we are kind of the center of the universe. Okay, that's not true, and I'm going to show you why in just a second. Messed up on that arrow too. Well, you guys know what I'm talking about. Okay, so close things aren't moving away very fast. Far away things are moving away very fast. And this is what you would expect if there was a Big Bang. This is what made people believe, this graph right here, that there was a Big Bang. Because you play this in reverse, this video that we have taken a snapshot from, and everything comes together in one point. That's the Big Bang, but you know, we're watching it now after it has been a long time since. Well, you might say, why would we be the center of the Big Bang? Well, I'm going to argue that we don't have to be. Imagine a hand grenade. Okay? Because we can. And imagine this hand grenade explodes, and then a short time later you take a snapshot of the pieces. Okay? So a very short time later, this hand grenade has exploded. Now, this one wouldn't have moved very far, because it didn't get very far in the time we waited between the explosion and when we took the picture. In fact, the further you get away from it, the faster you would infer things must have traveled or to get there. Okay, All right. But watch what happens. This should look familiar. That's what this is looking like, right? You get this pattern of velocities that gets bigger as you get further and further away from the explosion. But what if we ask, let's say, this piece right here, and just to make it simpler to see, I'm going to add a little piece here with an even smaller velocity, a piece here with the velocity like that, a piece here with a velocity like that. Let's put ourselves in the orange reference frame. Okay, so now Earth is like this orange dot. Okay, the orange reference frame sees this one traveling with it to the right, but away from it slightly. And so it sees a piece going like this. And it sees this one, moving to the right, but not quite as fast because the relative velocity is not as much, because it's moving kind of with it. All right, let's look at this piece. Well, it's moving to the right with it, but it's also moving down. Are you seeing what I'm seeing? Okay, this one isn't moving as fast to the right, and so in this reference frame, it's actually moving to the left. Well, look at that. You can plot these. All the pieces will look as if this was the center of the explosion. Every relative velocity will look as if it's, always away from that object. Now, lots of time has passed. And the reason you get some blue shift is that gravity is trying to pull this back together. We're going to find out that it's losing the battle. That is crazy, and that's something that we found in the last 2 decades or so. Okay, so this is evidence for the Big Bang. Everything seems to be moving away from us. But there should be other evidence. If the Big Bang happened, then you have matter forming out of this energy. There was just so much energy lying around that you can get matter formation, like we discussed with pair production, for example. And it kind of congeals into a universe with lots of space, some matter, but it's still very, very hot. It's so hot, in fact, it's a little bit like being inside the sun. You have this really dense plasma, and light can't get through that. The sun's opaque. It's just the surface is so hot that it's radiating light. So the sun doesn't let light through it. It just radiates light. Well, the universe didn't let light through it either. Any light that was emitted would be absorbed by the next little piece of plasma that it was trying to pass through. And so there's this time when you reach this critical temperature and pressure and density where the universe suddenly becomes transparent. So let's see if we can. So let's say this is the point that's going to become the sun and the earth, okay, our solar system. Imagine yourself in that hot, dense plasma, and it just became transparent. Well, there's no one with eyes to see at this point, but you get the idea. You could see this expanding shell where the universe just emitted its light and is now just getting to you. And that shell, after 1 second, would be 1 light second across. That's a second, not a year. Okay, so after 1 second, it's 1 light second across. After 2 seconds, it's 2 light seconds. Oh, well, okay. The radius would be 1 light second. After 2 seconds, the radius would be 2 light seconds. So people who were studying this idea of the Big Bang said, we should see this shell of light. But that's not true. You've gone outside and looked up into the sky, and you don't see this shell of light. They could even predict the temperature that the universe was when it became transparent suddenly. And it's roughly the temperature of the outside of the sun. So it should have been about 5,000 Kelvin, and we should see bright white light coming from every direction we look up in the sky. Okay, well, what they didn't remember is that everything is becoming redshifted. the further this shell gets away from us, the further this shell gets away from us, the faster the matter is that was emitting that, because it's redshifted. And so instead of showing up as a black body in the visible spectrum, like we would expect, it's redshifted all the way outside of visible, past infrared, and into the microwave region. This is such a high redshift that people weren't looking for it there initially. In fact, it's kind of a sad story. Someone told them to look for it there, and no experimentalists wanted to look for it. So we waited another 35 years or something before someone accidentally discovered this shell of light, which is now 14 billion light years. So 14 times 10 to the 9 light years across. Now, what's behind that shell? We don't know. You can't see you can't see past this edge of the universe, because past that, the universe was transparent. In fact, you don't even see stars forming until inside this shell, because it took some time for the matter to come together because of the force of gravity and start fusion and have that energy released as light. So it took a few 100 million years or so for that to start happening. But you look out at the sky with a telescope that can see in the microwave region of the electromagnetic spectrum, and you see exactly what the Big Bang predicts. It was this, it's one of the strongest evidence, some of the strongest evidence we have for a Big Bang, is that every direction you look, you see a black body spectrum, but shifted so that it's in the microwave. And this is called the cosmic microwave background radiation. So cosmic microwave background radiation. And it can help you model different ideas of how the Big Bang happened, and you can check that. You can also see, this is crazy, one of the reasons they send these expensive telescopes up into space to map the microwave background radiation is that there are small fluctuations on this sphere, and I mean small. We're talking about like 1 part in 10 parts in a million or something. That it's slightly hotter or slightly cooler, depending on what direction you're looking at. And you can basically see quantum effects, which is crazy. You're looking at the biggest thing we know, the visible universe. This is 28 billion light years across. And you're looking back in time so far that quantum effects were important. The small scale effects, because remember, this went transparent back when it was a tiny, tiny universe, and it has since expanded into this huge thing. It's pretty cool. Now, what if you were a person standing on a planet over in this region of the universe? Well, you would see your own shell that would just barely include us. You wouldn't see us because you would see the light that was emitted by this region of space right when the universe went transparent. That's what you'd be seeing right now. So the further you look away, the further back in time you're looking. Astronomy is like this cosmic history lesson, and the further an object is away, the further back in time it was for that light was emitted. I mean, think about this. Our galaxy, which I drew in rough approximation here, our galaxy is about 100,000 light years across from one side to the other. So light from the center of our galaxy has taken, something like 30,000 years to travel across that distance. Here we're talking about billions of years for the light to get there. Now, what if, who am I to say? I don't think this is true, but what if there is an edge to the universe and our sphere just hasn't hit it yet? this person may see an edge to the universe where there is nothing out there. So really, I should have just erased that side of the sphere. Does the universe have an end? It's one of the open questions of science. But I think, reading the scriptures, I'd say it probably doesn't. I think this is an infinite creation, whatever that means. It doesn't fit in my finite mind. The other things to know from this chapter, I mean, none of this stuff is really all that important for the test. But just remember black body radiation. The hotter something is, the brighter it is, for one thing, but also the higher the energy of the photons are on average. So that peak wavelength shifts into the visible and into even the ultraviolet for hot enough stars, for example. Trying to think of, I mean, as far as equations go, there's the one, the apparent brightness depends on something called the absolute luminosity, the absolute brightness. And then you spread it out over the area of a sphere, 4 pi, the distance to the star squared. So you have a certain amount of power emitted by the star. You spread it out over a bigger and bigger sphere the further you are away, and you can find out how bright the relative brightness of a star. Some stars in the sky look bright because they are bright, and some stars look bright just because they're close. I'm trying to think of anything else that I wanted you to know. One thing that you really should do is just Google this, Stellarium. It's a planetarium that you can run on your computer. It's Planetarium software. You can search for any object you want to see. You can turn off the atmosphere and see what our planet would look like, what it would look like to look up into the sky with no atmosphere on. You can do a lot of fun things with it. Just look it up. I don't know if there are probably tutorials out there that show you some fun things to do with it. But then we've got the Planetarium Show that we'll do as our final day of class. This, like I said, it's not really what I expect to test you on. That's mainly chapters 29 and 30, and maybe a little from 31. It's mostly just to see how cool the universe is.